Okay, can you hear me in the back right now? Perfect, thank you. So I'm Benedek Rozemberczki. I'm going to talk about deep learning for drug pair scoring. And before I start this talk, we are recording already, that's great. I wanted to mention that this talk is not going to cover anything that comes from Isomorphic laboratories. I'm really sorry for that, if you just came for that. It's going to cover papers that we wrote during AstraZeneca and machine learning libraries that we worked on in AstraZeneca. That's important to mention. Thank you. So the presentation covers ideas and some results from 3 papers. One of them is a survey paper from HCI 2022. There is a KDD applied paper that describes a library. I will speak about that library and more or less how you design a machine learning library when your end users are computational biologists and computational chemists. And finally, I will speak about a library and paper that is pretty applied, and we used it to do drug repurposing studies in AstraZeneca, mostly for leukemia. Okay, so the outline of the talk is the following. In the beginning, I will speak a little bit about what is kind of what we call as drug pair scoring. Then I will speak about chemical X, where I will describe how we operationalize all of those ideas that we came up with when we formulated this drug pair scoring problem. I will have some experimental results on that. And then I will speak about this model that we call Mumin. It's a tool to do repurposing and also to generate hypotheses of what are drivers of like cancer progression. And then we will have some experimental results for that and then some conclusions. Yeah. Cool. So drug pair scoring is a problem, very high level. The task is the following. Imagine that you have drug A, which is in blue, and then you have drug B, which is in red. So for these drugs, you might have some additional information that you are aware of, and that additional information comes from some biological context, and that biological context is given by a biological knowledge graph. In this case, I have some sort of simplification, and I depicted this as having, let us say, genes that are known to code proteins that interact with said drug. But it's not necessarily the case. You have a lot of freedom how you formulate it. But the point is that given those 2 drugs and the range of biological contexts or chemical contexts, your goal is to predict whether certain interaction happens or whether that pair has a synergistic relationship. And the way how you do it at a very high level is that you have an encoder for which you impute features of the drugs and some biological context. Then you have, after you have imputed everything, this trunk of the model outputs some sort of representation, which you can reuse later on. And you have a head layer which takes this representation of the drug pair, and finally it can take the representation of some biological context, for example, a cancer cell line, and you can make a prediction. So that's the task that you are trying to solve. Obviously, it comes with data where you have triples, where you have drug A, drug B, and some sort of context, and for that triple you have a label. So what's the motivation for this? Why are we trying to formulate this as a machine learning problem? And the reason is very, very simple. So if you just think about, let us say you have a database of 100 cancer cell lines where you are trying to, wow, that's great. Okay. So if you have a large database of cancer cell lines, let us say 1,000, and you have 10,000 drug-like molecules. If you want to do this scoring, you will have to do 10,000 squared times 1,000 screens manually, and that is not particularly great. So that has a lot of time cost. There are material costs for the assays and the screens. There are labor costs for this, and there are also issues with the tractability, whether you can do this in real time. So what you want to do is to pre-screen your existing drug assets against the various cancer cell lines. So there are 3 specific tasks that people usually formulate. One of those is drug interaction. The second one is polypharmacology. Typical setup is that you take 2 drugs, and there is an unexpected side effect that people observe. And finally, there is synergy, where there is this question of we take 2 compounds, and we observe whether there is a superadditive effect for killing cancer cell lines, or there is a subadditive effect. A superadditive effect is synergy, and that is particularly the thing that we are interested in. And finally, usually the output of these models is not used directly, but used in a multi-objective optimization model where we are trying to rank the drug pair given a cell line, and there are other aspects that you are interested in. So, for example, individual ADME properties, toxicology and physical chemical properties of the drugs that you are interested in. And our goal is to satisfy multiple objectives and find something that we would actually want to physically screen. So these models usually take 3 types of forms when it comes to the encoder itself, and that is the main differentiating factor. Let me explain. So one approach is the following, that we have that additional side information, the heterogeneous biological knowledge graph that we have in advance. And in that, we have nodes. We have a set of relations at edges. And out of those nodes, there are drug or molecule entities that we denote with calligraphic D, which are a subset of calligraphic V. And for those, we have a molecular encoder which takes some sort of molecular structure as an input. It's a parametric function parameterized by theta d and outputs a representation. So what I mean by this is that we discard the biological information that is here, and we are only encoding properties of the molecular structure for the drug. And this is kind of very lenient because this doesn't really rely on any specific formulation. So it can be, the drug can be described by a Morgan fingerprint. It can be described by a node feature matrix and a bond feature matrix, or a combination of those. Point is that this is the kind of the simplest model, but it doesn't give you any biological context around the ligand. There is another approach that people like to take. And if you know the paper, Decagon is one of those. Anyone is aware of Decagon? Marin Kazitnik, Yuri Leskovec, okay? So what they do is that they have this biological knowledge graph, and they create a representation based on systems biology. The idea is that each of the nodes has a representation itself, and there is some sort of aggregation function that can generate a representation based on a local neighborhood. That's the idea. So the representation is a function of an aggregation where there is a representation for each neighboring node around the drug. And then there is a third approach, and one of the things that we will discuss today belongs to this category, which is hierarchical encoders, where the idea is that each of the nodes has a representation that is output by a neural network that is parameterized by the parameters of a drug encoder, molecular level encoder, and you are doing message passing with that. So these are the 3 approaches that you generally find in various research papers. And what we will do is that we will focus on class 1 and class 3 in this presentation today. Cool. So how do we represent the biological context? It's very simple. Most of the times you have a set of biological contexts. This can be your set of cancer cell lines, for example, and for each of them, you have a feature vector that describes properties of that context. For example, you can have some sort of cancer cell line where you have a list of genes that are mutated in that specific cancer cell line that gives you a binary vector, and that's your input. And then you have essentially, again, an encoder which is parameterized by theta c, which is an encoder specific to that context. And then finally, for outputting a score for the pair defined on this drug set and context set, you just have this head layer which takes the input of the encoders that you had here. You have a loss function that is defined on the label for the pair here, and the prediction made for that label. And finally, the beauty of this whole thing is that the parametric functions can be trained jointly by minimizing the cost accumulated from the data point level losses. What I mean by that is that you can have a cost function where you are summing over all of the observed triples that you have, and you are trying to minimize that cost function. Is this clear so far? Yes, please have a question. Yes, I'm... Sorry? Yes, yes.
I'm actually a little bit confused. Could you please define all the variables? Like in the previous slide, I think there was an M.
Yes, yes. Let me explain. So imagine that M is a set of features that you can use. For example, you have a node feature matrix that you can use, for example, in a GNN. You can have an edge feature matrix that you can use in a GNN, and that set is specific to that drug. So it's very flexible. It's very high level, very abstract notation in a sense. Does that help?
Then M to the D means...
The M to the D means D is just, no, D in this case is just an index of that set. So it's the set specific to drug D.
Ah, I see, I see.
Does that help?
It looked like a power notation, that's why I was confused. Maybe you can also explain in the next slide.
Yes.
XC?
Yeah, XC is again a feature vector specific to a cell line, and in this case, instead of a set, we have something that is specific to that cancer cell line, for example, and it's a feature vector. Okay. Does that help?
Yeah, thank you.
Cool. Okay. So what we did is that in AstraZeneca is that we went and did a quite comprehensive literature review. And what we saw is that for the 3 types of tasks that you can have, interaction, synergy, and polypharmacology, generally you have a mixture of these models where you have, let us say, models that have a low-level molecular encoder. Sometimes you have these hierarchical models, and you have these high-level systems biology models. But it seems like that the main differentiating factor, at least for us, was induction, which is more or less the question of can I make a prediction for a drug pair where I haven't seen the drugs in advance and where I have a poor understanding of the system's biology. So what we did is that we realized that this is the main factor that is interesting for us, and with we decided that we will write a library for the lower level drug pair scoring models, and we will deploy that, and we will use that to extend the kind of like the product life cycle of the existing AstraZeneca drugs by creating pair combinations. Cool. Other than that, we saw that most of the models use, when it comes to the models that can incorporate systems biology, use drug entities and protein entities. That is super interesting for us because that means that if you have a large database, for example, of binding relationships between small molecules and proteins, you can build on top of that. And finally, people usually look at a smiles-based featurization of the drug. If you are unaware of what a smile string is, a smile string is essentially a serialization of the molecule on which you can either use sequence models, or you can have a featurization of the graph that you can extract from the smiles and create a fingerprint based on that. But what is very interestingly missing is any sort of geometric featurization, which is kind of rare. So if you want to write a paper in this domain, this could be an interesting thing to consider. Cool. So one of the big questions in this domain is how you design evaluation regimes. So one way to think about it is that you have on one side the drug that you are kind of interested in, one drug, and on the other side you have the other drug. And then you have the context that you are working with. And you have this data that you can think of as this large tensor where you have drugs in one dimension, drugs in the other dimension, and you have the outcomes. And the question is how you stratify your data to have a good evaluation regime. Generally, this type, so if we go by the rows this way, for the first one, random splitting that you see here, is pretty poor because it causes a lot of leakage on the drug side, molecule side. Based on the substructures, the model can just memorize, for example, that a specific drug is very likely to be synergistic. Yeah?
So Jess, I want to know that maybe I didn't get from your first slide that now we see that, for example, we have drug 1 and drug 2.
Yeah.
And then they have, what's the results that you say that is a significant result, or I want a result between two drugs? Like, what do you...
So generally, between two drugs, you can define multiple tasks. What we are discussing right now is not kind of like the outcome, or not, let us say, the target. We are just discussing that given a data set that consists of triples, where you have drug A, drug B, and the context, there is this issue of how you create a split in the beginning and how you design an evaluation regime.
And then what is like an example of that? Like you want to combine...
Yeah, so let me explain.
Oh, okay.
So I will explain that. So if you create this random split, it's essentially an IID split over all of the triples that you have, and it can cause leakage on both the contact side and the side of the ligand. If you think about it, for example, if the model can learn that a specific cancer line has a large number of synergistic combinations, then it's going to output that expected probability for synergy for everything. And that is not particularly good because the model is not learning to generalize. It's not learning to understand how certain mutations affect synergy. And the same thing holds for drugs. If you think about it, that if there is a very specific compound substructure that increases the probability of a synergistic relationship, then what will happen is that the model will just memorize that, okay, if I see this means that something is synergistic, even if it shouldn't be, and it's not learning the novel chemistry. So because of that, you can do kind of three things. One of them is a stratification by the chemistry, where what you are saying is that everything that is in white goes in, let us say, training, and everything that is in dark goes in, let us say, validation. And by doing this, you know that you are not going to leak information about the ligand. This is stratified on the pair, which means that the same pair always goes either in train, either in valid, or test. You can do this only on one side, or you can go and do a third thing, which is saying that I'm interested in understanding generalization for outcomes. What can we do about that? And for that, the solution is that you evaluate all of the pairs for a single outcome in your test or validation set. And of course, you can have, for example, variations on this, and you can combine these in ways that, for example, you would only evaluate on a block of drugs for a very specific target. But I'm just putting this out that this is like a very challenging area in the sense how you design your evaluations. Okay. The other thing that we observed, and these are models from this domain, from the last 5 years, is that people have a tendency to score these models with area under the precision recall curve or area under the ROC curve. And the reason for that is that in this domain, generally, you are not interested in hard decisions of yes and no, but you are interested in rankings. So the output of your model is usually not just that I will test this single pair on this cell line, but for a cell line, you're going to give to the laboratory 100 pairings that are interesting, and that is reflected in the evaluation metrics that people use, just to keep in mind. Cool. So, okay, we have this problem that we are trying to solve. We have a very high level understanding of what are the models that people try to use. And then in AstraZeneca, we had this need of having a tool for the computational chemists and the early discovery scientists to do this type of scoring easily as much as possible, and have a tool that they can load, and with a very basic understanding of Python, they can work with that. So first, we will discuss the library itself. So currently, I don't know how well it is maintained because I left AstraZeneca roughly a year ago, but there is an open source library that you can try out, and I will speak about this open source library, how we created this one, and why we created this library. Cool. So just to go back, we will focus on models that are at the molecule level, so there is no biological context, there is some sort of molecule that you are outputting and imputing to this drug encoder. There is a head layer, there is a number of application contexts. In this case, the pictogram shows polypharmacology, and then you are trying to score this as well as possible. So why did we go with molecule level models? One of the reasons was induction. So for example, if a computational chemist comes in with a lead-like molecule that is very close to become a drug, and for that one, we don't really understand the complete biology yet. We don't understand how it binds to, for example, various protein targets. It can still allow us to make predictions. The second property that is really nice, it's very easy to create attributions and explanations for a model like this. So I know that there are people here who work on explainability in graph neural networks. You can take essentially generic explainability tools out of the box and use those on top of these models. It's easy to pre-train them. You can just pre-train the drug encoder and you are done. Transfer learning is quite easy if you think about it, because if you have, for example, a drug encoder and a head layer trained for the cancer cell line example, where you have these binary vectors that describe the presence of a set of mutations, it's very easy to transfer that. And finally, you can have this kind of like structural ablations where you can ask questions of what happens if I remove this part of the molecule, how that changes the outcome. Cool. So how do we conceptualize these models that we will implement in this library? And if we do that well, the idea is that that can be very easily translated into code. And if we have a very high level, like meta model of how things work, then we can do that. So let me explain the mathematics in detail. So we assume that there is a drug feature set, which contains these molecular feature sets for each drug that you have asked about. So you can imagine XD as this set of these calligraphic MDs. Okay, is that clear? Cool. There is also a context feature set, which contains feature vectors for each of the contexts that you are interested in. For example, it can be 1,000 feature vectors for 1,000 cancer cell lines. And the idea is that you can look up this very easily. Yeah, thank you.
I would like to ask just about this process of extracting feature vectors from instances and from context. Is it something trivial, or is it something more involved?
Yeah, so you can imagine it as that for each of the drugs, you have this large key value store where each key is a drug ID, and the value can be, for example, a vector that describes the presence of certain substructures.
So, for example, you don't use, I don't know, multimodal feature extraction?
Yeah, you can. So again, this is some high-level meta model. But the idea is that if we can translate this well into code, this kind of meta model, then it's going to be very easy to, let us say, incorporate multimodal features.
Thank you.
Yeah, cool. And finally, we assume that you have this labeled drug pair context batch, and this consists of a drug index for the first drug, a drug index for the second drug, a context, and some sort of label. So you can imagine this as an oncology drug A, oncology drug B, a specific cancer cell line, and whether there is synergy or no between that pairing for that specific cancer cell line. And then the idea is the following, that more or less all of the models operate the same way, is that for the first drug, what you would do is that you would look up features that are drug levels. So it's a feature vector. You would look up some sort of molecular graph. You would have properties of the atoms if your molecular graph is this graph where you have atoms as nodes and edges as covalent bonds, which you might like as an idea or dislike. And you could have edge features. And you would make a forward pass and compute some sort of vector representation of that drug. So to answer your question, for example, this can be a very specific formulation of that. It doesn't have to be like this, and it's not necessarily something where you have to go with the molecular graph representation. You can also have, for example, specific information about the conformation of the molecule and so on. Okay. So what we can do is that we can do the same thing for the other molecule, so the other drug, and it's analogously the same process. The exception is that we have these like indices which are with prime. And we use the same encoder, as you can see, and same parameterization again, so it's the same encoder. And then you will have the same thing for the biological context. If you have that, you can have a head, and that head can make a prediction, and you can start to accumulate your loss in this cost. And if you have a library that can do this at a very high level, then the whole workflow for a computational chemist for training and using something can be way simpler. Usually these settings in pharma are not like having a large cluster where you train the model, then that model is properly deployed, but more like there is a computational chemist who has access to a Jupyter notebook that can access the GPU, and the target audience is kind of that type of people, the computational chemist for this library. Okay, so what we did is that we heavily documented it. We wrote a lot of unit integration tests, tutorials for them, like how can I impute my custom data set for the library. We set up CI/CD, and we have a lot of generic like software engineering elements of this, like linting, type hinting, and proper doc strings. So we did this mainly because there was no competitor at the time for this library. The idea was that in 2022, there was no library that can easily implement this whole thing in one go. Most of those libraries that were out there at the time in 2021, 2022 were running on PyTorch, which is pretty generic. The geometric deep learning libraries are most of the time not particularly drug domain specific, and they are not designed for drug pair scoring, so there was very clearly an opportunity for us to design something internally and to use it externally. Cool. So if we look at the models of what are the models that people used in this domain. What you see is that you have models for interaction, synergy, and polypharmacology, but the funny thing is that if you essentially change the head that you have, you change the loss function that you have, the same model can be reused most of the time. So there is no like question of how you do this. And of course, the encoders can be vastly different. There are a lot of models that are designed for operating on feature vectors, such as, let us say, Morgan fingerprints, and there are models that operate on molecular graphs, where you have a graph defined by atom nodes, you have the covalent bonds, and you have various features of the atoms and the bonds. For example, let us say, besides the an encoding of the atomic number, you could have things like, does this participate in a aromatic ring, yes or no, that type of node features. Okay, so the idea is that people who use the library, so I'm going to show some code, have a loader that they can use, and the loader gives you three things: a context set, a drug set, and the triples. Just to go back to have an understanding of this. So this is the drug set is something that is very abstract and we defined here. You have the context set and you are iterating over the triples that are labeled in a batch. Okay, so we are implementing this very verbatim code-wise. Cool. And then what happens is that you have a generator that will create batches for you. And the process that I had shown in the previous slide is going to be batched. So we are not going to do it for the individual triples, of course. And we can decide, for example, whether we want to have the context features used, whether we have drug level features that we will return, and whether we will have drug molecules for which we have molecular graphs. Cool. So this is the generator. And then what you can do is that essentially you can use Torch, you can take chemical X, and you can very easily define a model. This is a very famous model from 2018 that was designed to predict the synergy of oncology drugs for cancer cell lines. And then you can set up very easily a model where you took this model, you parameterized it, and you have a workflow that looks like this. Altogether, this is 20 lines. So instead of using PyTorch geometric, the comp can just go and take all of these things. And then what you can do is that, for example, you have this model that was previously trained on a custom data set, which is drug combination DB. And you have your own internal data set that you decided to bring in, which is for oncology drugs, specifically targeting leukemia. And you can score all of those pairs that you have in your little data loader. And based on that, essentially what you are doing is that you change the label triples in your generator, and you can, again, iterate over all of the data and make predictions. And then finally, you have this pandas data frame, and you can, for example, sort it and take the top 100 predictions and send it off to someone who can actually run it in a laboratory. So yeah, the library is able you can accommodate, for example, bringing in your own data, which means that you would have a set of triples which have labels, context set with features. So for example, again, somatic mutations on the cell line, and finally you would have a drug set with smiles. So I will show a few experiments. It's going to be, yes, sorry?
Yeah, just before we move to the experiments bit, can you tell, I was curious about two things. One is when you do a backward pass through the model, which parameters do you update? And second is, okay, so this is the first question.
Yeah, so what happens is that you can decide whether you want to update, for example, the head parameters or just parameters for the encoders. It's completely up to you. For example, if you have a large generic database on which you have trained, what you can do is that your company can call it a smaller one, and you can kind of leapfrog to that local problem. So you can think of it like that. Let me get a general understanding of how drug synergy works on all of the cell lines. Then let us generate internal data. Let us freeze out the layers, the encoder layers, and fine-tune the head for that very specific problem. It's very widely done, and a lot of people, especially, let us say, in biotech, and I'm one of those people who believes this, is that we can't really solve the problems generally, but what we can do is to get a general understanding for solving the task, obtain some data, and then fine-tune on that. And that seems to work. So not just on this problem, but on a wide range of early drug discovery problems. And what's your other question?
Yeah, the other question was, can you discuss the scoring methods a little, because I've not seen...
Yeah, so for example, the scoring itself, you can imagine it that it's, first you have a regression value that essentially estimates the slope of a surface where you have drug A, drug B, and you would have a measure of how effective you are at killing at the cancer cell line. So they literally pour the drugs over the cancer cell line, and what they are measuring is cell line growth. And the effect that you are looking for is having a superlinear effect, which means that it's like super additive. So let us say you would look at one dosage, what would be the, I don't know, cell line growth rate for one drug. Then you would look at the other one alone. And then the question that you are asking is that, is this an additive effect? If it's additive, then there is no synergy. And if it is super additive, there is synergy. And there is a third case where we say that, in fact, the two drugs, when they are combined, do worse than they would do alone. So, yeah. Is that helpful?
Yeah.
Thank you. Okay. There is another question. Cool. Yeah.
So you mentioned that you work with a pre-trained, fine-tuned paradigm, and for domains there is usually some domains are out of distribution compared to what you have been pre-training on, especially for vision, domains like vision. If you're fine-tuning for medical images, then that's considered out of distribution. So I was asking if there is a similar or relevant concept for this as well.
Yeah, I would say that one of the examples, I will give you an example from another domain within drug discovery.
Yeah.
So one of the domains is, for example, understanding of stability of a crystal structure between a protein and a small molecule binder. And there the data has a very interesting skew, namely that most of those proteins for which you have data are coming from so-called kinases. It's a class of proteins. And then you have other classes of proteins where getting a crystal structure is really, really hard, for example. And there, what you can do is having a general model and then fine-tuning for that specific class. So I would say usually, yes, the goal is the same, that it's kind of out of distribution.
Okay, thank you.
Yeah. Cool. Is it just my laptop or all of the presentations were like this? I'm just asking. Mine, oh, I feel honored. Okay, so what we did is that we integrated a few very common data sets that are from different tasks. So the two sides is a polypharmacology data set. There is drug bank DDI, which is an interaction data set, and there are synergy data sets. And if you think about it a little bit, you have a drug set and you have a context set. So for two sides, which is this polypharmacology data set, we reduce the number of symptoms to be the most common ones. And the number of labeled triples that you have, as you can see, compared to the overall number of labeled triples that you have, is quite low. If you would multiply the number of drugs with itself, multiply it with the context, you get a number, and if you compare that number to what you have here, it's kind of pretty lean. And this is very common, so if you think about this kind of like this tensor of data, it's going to be very sparse, and in certain like locations, it's going to be very dense. And there's going to be this extreme inherent bias of how people obtain data. And one of the reasons, for example, is that for polypharmacology, you have symptoms that are extremely rare. You have also drugs that are hard to manufacture. And for synergy, you can think about, for example, issues like that obtaining a cancer cell line and paying for it can be vastly, vastly different for something that is rare. And it can be very cheap and easy to obtain something that you can propagate anywhere where you want to do it. So what we did is that we created a structured split where we are evaluating just on certain holdout, kind of like these environments of context and drug pairs. And one of the interesting outcomes of what we had here is that we have models which have a very simple feed-forward architecture. So we re-implemented those models from the paper. We set those hyperparameters that the authors used. And what we tried to answer is that are those molecular encoders that use the molecular graph do better than using a feed-forward neural network with a Morgan fingerprint? And it turns out that more or less in this domain, a lot of progress that we made in the last, let's say, 5 years, you can't really reproduce the results with the graph neural networks. And this was in line with results that other people obtained. So what we did is having 10 separate runs with the hyperparameter settings from the paper on this very specific structured split. And the main result is that you can't really reproduce the results of the GNN papers. They are not as good in a sense. Cool. Then what we looked at is also training time. So we were interested in making a single epoch on drug bank DDI, and we, yes, please, there's a question there.
So if I understand correctly, using a graph representation of the drug doesn't improve upon Morgan fingerprint. Do you have any ideas why that might be? Is it because the methods weren't particularly good, or do you think this information is actually relevant for the problem?
Yeah, I feel like that the graph, so if you think about graph neural networks, what they do is that they kind of like create these Weisfelder-Lehmann trees and they are counting those. And compared to that, the Morgan fingerprint featureization uses something that can be chemically relevant. I don't think that the message passing paradigm without, let us say, incorporating geometry should do well on any type of molecular like ML problem. Yes?
So 2 questions. One about the architecture. I don't know if you are going to talk about it later, but I'm especially interested. Have you ever considered using some kind of graph transformers with sparse attention while processing the context feature?
This work doesn't consider that, but I can imagine that that is a meaningful representation. I feel like that what I see in the next 2 or 3 years is going in a direction where people use geometric transformers with some additional information on top about the covalent bonds. And the geometry would come from various conformations that you can get. But again, this type of modeling doesn't really consider the geometry because there is no, how to say this, real understanding of why a specific ligand would bound to that protein that is mutated, and it would affect that, and the other drug would, for example, bound to another protein that you have. Does that make sense?
Yes, but...
so the biological information that you're using in the context is not enough well described to have an approach where there is meaning for geometry.
Yes, this is why I was rather interested in transformers here, not exactly geometrical transformers, because like I don't know how far you try to push forward with using all the context information available.
Yeah.
So that's my question actually. Did you just use graph neural networks and that's all? Or?
Yeah, it just uses the graph neural network with a pretty standard torch drug featureization that we can use.
Okay, and the second question, rather trivial one, did you really re-implement all those methods from papers from the scratch?
Yes, yes. I would say the highest level implementation that we used was for the GNN specifically.
And why exactly? Weren't they available just for experimenting?
So yeah, so some of the papers had, let us say, Keras, others had TensorFlow, and so on. And what part of this effort was the unification of having the layers together. Yeah. Okay. So training time-wise, what this shows you is that batching is not something where you can have like a drastical improvement. Keep in mind that these are in log scales. So let us say just because you are able to increase your batch size by multiple magnitudes, you are not going to have some drastical like drop in the runtime. Keep in mind that this is log 2 and that is log 10. Cool. Yeah. So what we were also interested in is doing inference, and what we wanted to try out is what happens when, let us say, in an environment like AstraZeneca, where you don't have a large number of GPUs and people are only able to run something on a CPU. What happens when you have to score all of the environments in DrugBank DDI for all of the drugs that you have in a set? That we sampled from DrugBank DDI, and we looked at the runtime, and what this means that still in very limited time, a computational chemist, if you think about this is roughly 1,000 times 1,000, can screen a large number of compounds with something like this. Cool. So some conclusions. So actually, Chemical X itself, both the polypharmacology modeling and the synergy modeling is used for targeting hematological malignancies. So AstraZeneca has a pipeline which has a large number of these types of drugs that target that class of cancers. The issue, if you know leukemia, is that generally like there are two main types of leukemia. For one, we have very effective medication. For the other one, not really yet. And a lot of early oncology computational chemists are using this library in their day-to-day work, the internal version. It was really fun to work on this because we worked together with people from Harvard and Vanderbilt University. A lot of people who worked on this library actually are not machine learning engineers or machine learning scientists, so people on my team who were interested, they were able to use this. And one of the things that we could improve is that a lot of effort lately in molecular AI goes into how we generate a split, and one of those ideas is scaffold-based splitting, where essentially you don't just split the drug set based on the drugs, but you take into account some sort of coarse clustering of the drugs. And one of the ways to achieve this is what we call a scaffold, which is essentially the molecule. You take the molecular graph and you break it down to rings and linkers between those rings. And that's one way to define this clustering. And finally, you can have the geometric graph encoder. So that kind of ends the first block, and then I will talk about something else where we try to incorporate the systems biology in this. Are there any questions in this block? How are we doing with time? Do we have 30 minutes remaining or more?
I think we have 35 minutes.
Thank you. Okay, so let me start this again. Okay, so this paper came from the idea that AstraZeneca has a very large effort for which it is well known to build this large heterogeneous knowledge graph where you have biological and chemical entities as nodes. You have connections between those entities, and this is mainly used for drug repurposing studies and also for target identification. I don't know how much you know about these tasks, but these are very basic drug discovery tasks that someone tries to solve. So what's the motivation? We want to solve the synergy scoring problem, and we want to find those pairs where you have a superadditive impact on the cells. For the cell lines, we have these phenotypic screens, which describe essentially a set of mutations. And it's important to note that everything that we do is something that operates at the cell level, which is a very poor proxy for the actual synergy. Because a large number of drugs that people try to develop nowadays are so-called immuno-oncology drugs that for which you can't really have a good, let us say, characterization at the cell level. So this is quite well suited for so-called targeted medications and not for these immuno-oncology medications. The idea with these drugs is that they will bind to certain proteins that have very specific mutations, and this is why modeling this at the cell level is kind of great. We also wanted to use this internal biological insights knowledge graph, and we wanted to do repurposing. Repurposing is kind of like this holy grail in pharma, because you can think of something that you have a product that has a life cycle. People will try to kind of like improve upon that drug. If there is a patent for that drug, people will try to look into kind of breaking that patent in a sense that they want to have a molecule that is sufficiently dissimilar from your molecule that they can patent it. But it is, let us say, has a higher efficacy, lower like toxic effects, and because of that, by meaningfully pair repurposing, by finding a good combination for a drug, it's kind of something that is a holy grail. You can keep your market share, and there's a lot of like business meaning behind why you want to do this. Cool. Okay, so what we wanted to do and how we wanted to model this problem is, just let me go back one slide, is to incorporate biological knowledge. So from now on, we will be in a setup where we will have the following input data. We will have information about the drugs, drug features, and we will also have features of the proteins that they interact with. So you have this bipartite graph of protein-drug interactions, and the goal is to solve, again, this synergy scoring problem. And there is a lot of freedom here if you think about it, because you can featureize your drug as you wish. So that's one thing that you can do. And you can featureize your protein as you wish. So you can go with information about, let us say, the primary structure. So you can have, let us say, a protein sequence encoder. Or you can go with secondary structure where you have already some sort of annotation about the secondary structure of the protein. Or you can take, let us say, a prediction made by AlphaFold, and you can create a proximity-based graph that you embedded in advance. So there is a lot of freedom how you do this. Point is, two types of entities, proteins and drugs, and we are trying to predict synergy. Cool. So one of the things that we were really interested at the time is how other people are solving this, and it seems like that going with the drug and protein nodes both is a reasonable idea. A lot of people did that, understanding those interactions in a context, and also adding additional features and not learning some sort of vector from a trainable embedding seems to be something that is novel. So we will operate on a drug pair synergy set. It's defined on set of drugs, set of contexts, and we will have these binary labels. And we are going to score this, and we are going to do that with a parametric predictor that depends on kind of like the drug indices and the context index, and it's going to output a propensity score for us. And we are going to have this drug-protein interaction graph where we have a node set that is the union of the drug nodes and the protein nodes, and we have edges between that. That's what we will start with. And again, we are using some data set that we collated. We will use a data set that we collated in AstraZeneca from external sources, but we also have internal sources for this based on certain types of screens. We know what binds to what. Okay. So we will go with, and you will dislike this notation because the D is not as a superscript, but what we are doing is that we have a drug encoder that is parameterized by a set of parameters for that type of entity. You have freedom of how you choose it and how you operationalize this. You have a protein encoder that operates on features of the protein. And then you have a simple vector representation of the cell line that you are operating on. And then comes the question is that these are kind of like individual informations about these kind of like molecular entities and biological entities, and how do you incorporate the systems biology information, how things interact with each other is the next question. Cool. So what we did is that first let us observe that because we have a bipartite graph, there are no interactions between drugs themselves, and there is no interaction between proteins. That's one of the things. And another thing that we can note is that if we take a random walk on this graph, then what happens is that when you are at even steps, you are going to, and you started from a drug, you are always going to hit drugs. And if you are at an odd step, you are always going to hit proteins. And this can be kind of interpreted quite well, because what this tells you is that at the 0s scale, you are talking about the drug itself. When you are at the first scale, you are talking about the proteins that it binds to. When you are talking about the second scale, you are talking about essentially drugs that bind to the same protein, and you can have all of these interpretations of these various scales that you have. And then what you can do is that, let us say that you have been able to obtain a representation for all of the entities that you have, both drugs and proteins that are both part of this set V. Then what you can do is that you can essentially concatenate the representations that you get at various scales. At each scale, you get a representation by essentially averaging out the representations at that scale using a weighting scheme that comes from the random walks. And this kind of gives you an increasingly large view of what is the biological context that you are operating on. Of course, this might be a suboptimal weighting scheme, so you can come up with other ones, but this is kind of simple to implement, and it's very, very simple to come up with a approximation scheme for these probabilities, because if you think about it, if from any given node, as the scale that you consider L is sufficiently large, then you are going to have this view on the graph where you are essentially averaging the representations over all of the other nodes, and that is suboptimal, because if you have a large bipartite interaction graph, then what happens is that you are going to struggle just with the averaging. So we will come up with an approximation scheme for that. But finally, what happens is that we take these multi-scale representations for the first drug, the second drug, and the cell, and we will concatenate them together. So again, both of these give you a lot of information about biological context. For example, if you have one of these drugs is a kinase inhibitor that binds to everything, it's a promiscuous binder, it's going to tell you a lot of information about that. If the other one is very targeted, it's going to give you information on that. And finally, you have the context information. Again, you have a scoring head. You have some sort of loss function that you aggregate over that labeled triple set. And you are more or less done with this setup. There is an issue of how you approximate MD and MD prime. And I'm not going to get into the details of that. What we did essentially is that you can have truncated random walks that you are running. And at each scale, 0s, first, second, third, you take a fixed number of samples around that node, and you can just look up the representation of the nodes that you are hitting, and you can average that out. And one of the things that you have to see that this is kind of interpretable in a sense, because the information that comes from odd and even scales is alternating between drugs and proteins, and based on feature importance, for example, you can tell when the model made a decision that whether it was the information about the drug itself, the context that comes from the proteins, or the other drugs that mattered. Cool. So we run a large number of experiments, and this is going to be an interesting experiment because I can talk about some other result that is, in my opinion, pretty cool, but just a little bit of context more, some empirical observations about the data itself. So if we look at how over the common cell lines, the 5 most common cell lines that you observe in the data, the ratio of actual assays and experiments is distributed, what you see is that 40% of the data comes from one single cell line overall of the data that we were able to use. And this is kind of reasonable because certain cell lines are very easy to propagate and very easy to obtain, but you have a massive bias. And you also have an issue that if you would have a representation of the cell lines that is learned, a learnable parameter vector and not some extrinsic parameterization described by a feature vector, you wouldn't be able to generalize. Because most of the times you would be kind of updating weights for this cell line. The other thing that you see is that certain drugs are widely tested. It's also based on availability, so it's good to keep in mind. And some other empirical observation is that a lot of, for example, if you have a drug pair that you have tested at least on 7 cell lines, then in 80% of the time, there is going to be a conflicting pair with what you have observed. What I mean by that is that if you have tested a pair of drugs for a specific cancer cell line 7 times, 80% of the time you will observe that there, let us say it's always synergistic, but in 80% of the cases you will also observe that it's actually fueling cancer growth instead of slowing it down in a synergistic way. The other thing that we see is that this is quite common for breast cancer and ovarian cancer. So a lot of those drugs that people test for these types of cell lines where the tissue is coming from have this kind of pairs, have this property that a given pair can be very beneficial for targeting a cell line, and at the same time it can be kind of pretty problematic. Cool. So some empirical results. So what we did here is that we have our existing structured split, and we are trying to take out a small chunk of the training data. Yes, who's the question? Yes.
So in the last slide, you showed this conflict. How do you deal with it?
What solves this is that you have an understanding of the biological context by having the context vector. If you would just say that I test the pair without that biological context, then, and you would have a model that doesn't have this local information that we are operating on this cell line tissue, you would end up with a model that can't really handle this. This is just an empirical observation about the data, why we need a context vector. So instead of, if you would go with a model, let me show this, where you don't have this encoder, and you would just go for drug synergy, then you would hit the problem that we observe here, is that if you don't have an understanding of this context that is cell line specific, your model would be kind of most probably overfitting to the majority output by that pair. Is that?
Okay, so there is no conflict in the experimental result. So if I do the same context, same drug pair, one of them is showing a positive response, one of them is showing a negative response, that is not happening here.
That can happen. Of course, experimental data noisy. Yeah. What I'm just saying with this is that you need local models.
I see.
Yeah. Cool.
Thank you.
Okay, so this is a super interesting result. So what we see here is that with very little data, you can have a very nice performance on the holdout that we have. And this is quite common in drug discovery, that things become really flat pretty early on for these types of plots where people try to run evaluation. If this holdout is not so what we are trying to do, sorry, just to reiterate, if the data that you are using for training is not stratified by the ligand clusters, you are going to observe this, because by creating an IID split for subsampling the training data, you are essentially going to see most of the ligand clusters very early on that you can learn from, and you don't really observe any sort of scaling law that you would observe otherwise. So one of the things that I feel like is important is that by adding a setup where you can have an evaluation that is based on clusterings and not just IID splits can help. However, what this also shows is that when you have additional information in, so this is an IID split that comes from biology, that can kind of change the nature of the scaling law that you are observing, so it doesn't flatten out that fast. Kind of that's what we are trying to show here. Cool. Yeah. So one of the things that was also a question for us is how you, how to say this, do when the pairs are very, very different from each other. So this, what you see here is the two lead-like molecules are such that both of them has a molecular weight higher than 300 Daltons. So these have been pretty much in the pipeline for optimization. And fragment means a molecule that is very tiny, and it's very early in the discovery process. And what we are doing is that we have 3 different scales that we consider. We look at the ligand itself, interacting proteins, and ligands that also interact with the same proteins that the source ligand interacts with. And what this shows, in my opinion, quite well, that fragments can gain a lot of performance just by understanding the biological context, which is, in my opinion, a quite nice result. And it is a good question, what is the right way to interpret this result? In the sense that most probably for most of those fragments that we have, the model has very little to start from. So you can imagine it is that you have this scaffold, which is very tiny, has a very little functional groups on it. And because of that, initially the model that you have doesn't really have sufficient has sufficient information to start from. So you can think of it like I give you this Christmas tree that I have removed all of the beautiful bulbs from, and what I'm asking from you that how does it work in a certain situation, you are not going to know a lot, but if I tell you, let us say, other things about the environment of the Christmas tree, you will be able to tell way more about it. Cool. So there was another question that we were interested in, is namely that how well the model does across various types of cell line tissues. So obviously you have practical use cases in mind, not just a single number. So these are the source tissues that you can have. And we can see that there are radical differences in how the model behaves. First of all, at various scales you have gains that can be rather negligible sometimes, but we have evidence that adding information about the proteins helps. And also we have evidence that this affects different types of cell lines differently, which in my opinion is again an interesting outcome of this. So again, having global models might be problematic. So for example, in this case, I believe someone there had this question, a paradigm where you have very specific data for hematological cancers could help. Cool. So one of the things that we observed is that there is already early clustering based on the trunk representation. So in this case, the trunk representation has this form of multiscale drug representation for drug A, multiscale drug representation for drug B and the cancer cell line. And we observed this early clustering, and that is kind of the result of 2 things. One of them is that there are going to be drugs that are have a higher probability than the average probability to be synergistic. And you observe the same with cancer cell lines, that there are going to be cancer cell lines which have a large number of synergistic combinations. And finally, a third reason for observing this is that certain cancer cell lines share the same somatic mutation. So you can think of them as that you have a set of features and you branch off from that and you do a little bit of modification on that. So yeah, what we did is that this data that we used to train this doesn't overlap with the NCI almanac completely. And we scored against the NCI almanac a very specific drug that we were interested in, vemurafenib. And what we were able to show that the model in the top 10 in the bottom 10 was able to recover a reasonable number of synergistic and antagonistic labels, where antagonism means this relationship of actually being subadditive. Okay. So yeah, one of the things that I mentioned is that we can, of course, compute the random walk transition probabilities exactly, but we can also have an approximation. So what we can do is that as the number of random walks increases, we can observe that as we get a better approximation of that multi-scale representation, we are doing better on the synergy scoring task. But we can also see that the gains that we have are becoming kind of like insignificant if we think about it using the box plots. Okay, so yeah, and then there is another question that we could ask is that as we change the size of the batch size, and as we change the number of samples that we take in the random walk approximation, how fast this is relatively compared to the exact computation. So what you see here is that when something is above 100%, it means that the approximate computation is actually slower than the exact one. So the sweet spot, if you want to be fast, is around like, I don't know, 2 to the 5 samples in a batch that has a large number of drug pairs with contexts. So yeah, the conclusions of this is that Mumin is used in some of the AstraZeneca multi-objective optimization systems, again, for hematological cancers. We designed a very simple SHAP-based scheme to approximate the relevance of proteins that participate in driving some sort of resistance. And there are a lot of other things that you could do. So in this model, if you think about it, let me go back. The entity representations that we created are vector valued, and that could be replaced. So you could, for example, have a representation that is matrix valued, for example, for each of the atoms that you have. We operate on 2 types of biological entities, drugs and proteins, but that can be extended. The relation types between the proteins and the ligands is not particularly modeled. There is no conditional weight matrix for various types of relationships. And of course, this task could be combined with other things such as polypharmacology modeling and drug interaction modeling. And you could have a setup where you don't just focus on the cancer cell lines, but other types of outcomes that you are interested in. So thank you for the kind attention. I don't know how we are doing with time, and I've put together a large list of references for everything. So I will send this to the Slack channel if people are interested. Thank you.
Thank you very much, Benedek, for this brilliant presentation. We are actually doing quite all right with time. So we've got around 10 minutes for questions. And actually, I was interested in something you said during your presentation. You said that in AstraZeneca, you used data sets from external sources, right? And I've heard that it's quite difficult to obtain them. So yeah. How did you manage? Was it due to some project?
No, so yeah, so most of those data sets I will also send a link to the Biological Insights Knowledge Graph that we incorporated there are proprietary. And one of the reasons that we have a paper out of the knowledge graph and not a data set out in public is that we have a lot of proprietary data sets. In fact, we had I believe the data budget was larger than the labor cost budget for our team.
Okay, that's understandable. Thank you very much. All right, so now it's time for some more questions from the audience. If anybody wants to ask something, please raise your hand. Probably because we were speaking a lot and asking questions during the presentation, it's quite clear. All right, we have one here. So let me get to you.
So you had one slide where you showed all the different models you used, and you had some GNNs there, but something that confused me was that all of these are basically not higher order GNNs, so these are all kind of GNNs that are, as you said, as good as WL. So is there a reason why there are no fancier GNNs?
No, what we wanted to do is that we wanted to evaluate these models as they are, because this model was actually used by early computational oncology in AstraZeneca, and we were interested whether with the existing, let us say, modeling that is out there, you can model this. Yeah.
Okay, so you were just interested in seeing how good the stuff that exists is, and not just beating the stuff that you.
What I'm trying to say here is that in industry, in this case, those people who let us say were using this, they are super skeptical. And you have to show that you can have an actual gain. And again, I would say that so their set of technical skills is different from that of someone who is in machine learning. And because of that, getting through that, hey, you could use something that is like, I don't know, not Weisfelder-Lehmann 1 is really hard. Yeah.
Okay, thank you.
Any more questions in the audience? Okay.
During your presentation, you mentioned that there's a difference between using GNNs and embedding the geometric information. This is probably related by my unfamiliarity completely to chemistry, but I thought that describing the graph was already like introducing some sort of geometry information into the...
Yeah, you can think of that, but one of the things that you have to take into account that molecule for which you have, let us say, the two-dimensional drawing is completely flexible and can take a large number of conformation of what shape it takes. And when you have a generic GNN, that can't handle that geometric information that you can get by the various conformations.
Okay. But in the GNN, I can also encode, for example, the relative angles between atoms.
Yes, but these are non-geometric GNNs that people are using. So imagine that most of this field, what people do is that they take a graph neural network, they take the molecular graph without any spatial information. They have additional node annotations. Let us say, is it part of some sort of chiral center, whatnot?
Okay.
And that's what they are using, yeah.
Okay, okay. Thanks.
But if you think about it, I believe there was a question. If you think about it, on the, let us say, on the cell line side, you don't have a good description of some sort of spatial system that you are trying to, let us say, find an optimal position of the molecule binding to one protein that it kind of inhibits, then the other one will bind to another protein. But you would need that type of data to meaningfully use a geometric approach, in my opinion.
Okay.
Okay, another question here.
Can I take another water meanwhile? Because...
Okay, so this is more of a general question, not entirely focused on the presentation, but so there's this trend in some labs in the world that they are trying to extend like graph neural networks to higher order structures, such as, for example, hypergraphs, or even higher. And I was just wondering whether, so then there's also this discussion of whether like modeling a problem in a higher order structure is actually feasible. So my question would be, in industry, so does one just use for example, as you said, geometric graphs? Is that like the limit, or does one actually try to model higher order structures as well?
Yeah, so I will give you an example to that. I would say I had a huge disagreement on that. So what people do in these biological knowledge graphs is that they take biological pathways and they model them as this supernode that is connected to every other biological entity that participates in that path. But if you think about it, by doing that, you created the shortest path for that biological pathway, where the pathway starts. In one hop, so first entity that kind of like at the edge of that pathway, you hop to the pathway and suddenly you are at the end of that pathway. And in that case, if you think about it, this supernode-based like representation of a pathway is not practical. So what is a pathway in that case, for example? Is that a group of nodes and edges? Is that some sort of like, let us say, hyperedge? I feel like that besides these questions as a machine learning question, there is also the question of like, what is the data structure that can optimally represent this, which is a completely different thing, yeah.
All right, I don't see any more raised hands, so I believe that we're quite okay with time, that we're done with questions, and yeah, okay. And because we've had a bit of move up in our schedule, and our next speaker is very gracious, so she will graciously start 15 minutes later than in the original schedule. We now have a coffee break, that's half an hour. So we see each other at 3:45, I believe, yeah. And thank you again, Benedek, for this presentation.